or while we're waiting for 2 minutes, and since we're on anyway, I'm going to go ahead and ask one of my questions.
Okay.
One of the things I really like to hear is what do you like about PL research?
Okay, sure. So what I like about the kind of PL research that I do specifically is that it's kind of a soup to nuts thing. Like, I like proving theorems, and I like writing code, and I like building systems, and I like talking to users, and I like doing design, and I like solving problems. And I can do all of those on a single project, right? I can design a language and prove theorems about its properties and do its implementation and talk to users and get an experience, do the design process. I really like that I don't have to choose do I want to be a theory person, or do I want to be an implementation person? Do I want to be a design person? I can be all of those kinds of people in the context of a single project. Plus, I just like languages. Yeah.
Yeah, that was one of the things that always really attracted me to compilers. It just seems like it interacts with so many different layers of the abstractions that we work with in computer science. And so it's really nice.
Right. Yeah, in my spare time, I study Italian. Like, ho studiato italiano, studiavo italiano da studio italiano da 16 anni. So I can't quite speak it yet, but I'm, one of the things I do in my spare time is study a human language instead of a computer language. So it's just, there's something about languages that appeals to how my brain is framed.
Excellent. Well, I'm going to go ahead and officially start now, since we've done kind of a warm-up question already. I am quite honored to be hosting Kathleen Fisher in her Ask Me Anything session. Kathleen Fisher is a professor in computer science in the computer science department at Tufts. She's also the department chair. Previously, she was a principal member of the technical staff at AT&T Labs Research, a consulting faculty member in the computer science department at Stanford for a while, and a program manager at DARPA, where she started and managed the HACMs and the PPAML programs. Kathleen's research focuses on advancing the theory and practice of programming languages and on applying ideas from the programming language community to the problem of ad hoc data management. So the main thrust of her work has been domain-specific languages to facilitate programming and managing those massive amount of ad hoc data that we're all having to deal with. And so this includes systems like the Hancock system and the PADS system. So more recently, she has been exploring synergies between machine learning and programming languages and studying how to apply advances in programming languages to the problems of building more secure systems. Kathleen is quite distinguished. She's an ACM fellow, and she's also really given back to the community. She's been in the program chair for many conferences. In this bio, I noticed that it's actually missing the fact that she was PLDI 2019 program chair. And she's also been general chair for things like ICFP. She's also been the chair of SIGPlan and the co-chair of CRIW, and is now an associate editor for Topaz. So thank you so much for agreeing to do one of these Ask Me Anything sessions. And I'm really looking forward to hearing your answers to some of these questions. So I'm going to get started on the questions that people are posting in Slack. Please do post questions to Kathleen in the thread devoted to this AMA session, and I will start asking them. So the first question is from John Wickerson from Imperial College London. It says, you're somebody with a lot of experience of chairing conferences and the like. Do you think we should aim to return to PL conferences as usual once the pandemic is over? Or would you support reevaluating how they are organized so as to make them more accessible and more environmentally friendly?
Good question. I don't know. I think some of it depends on how long the pandemic goes on and how well we learn to cope with meeting each other remotely. I think that we've done a lot better remotely than I would have expected. I think a lot of tools came online just in time. Like if we were doing all of this with video conferencing tools from 5 years ago, we would be much less happy than doing it now. Obviously, there's still glitches now, but it's much better than it was. I think like the Gather kind of tool is not yet quite ready for prime time, but it will obviously improve dramatically in the next few years. And those kinds of tools make it much easier. I think to some extent we can get away with doing it online right now because we have a lot of the relationships built over time and having spent time in person. I personally would be sad if we only had online things going forward. Some of my closest friends in the world are distributed all over the world because of meeting with them over courses of a lifetime in conferences, and it would be sad to lose that connection. I think so. My hope is that we end up with some kind of hybrid approach in the future where we can get some of the benefits of in person and online. I think that that's the absolute hardest case. Purely in person is one level of difficulty that we know how to deal with and has the known advantages and disadvantages. Purely remote is something that we're learning how to deal with. And that in many ways it works better than having a mix of some in person and some remote. For example, like my department, our faculty meetings work much better having everybody remote or everybody in person. But when you have some people remote, the people who are dialed in are just second-class citizens. So I think we're going to need to figure out how to make it so that people who are remote get to be first-class citizens. And maybe there's technical solutions that need to come into play there as well. And we'll have a lot more expertise about how to do that for our pandemic-enforced group experiment. So I'm hoping that we'll end up with a hybrid. I'd be sad if we only had online meetings going forward.
Yeah. Do you have a current conference that you're chair for or program chair for that you're planning right now?
Nope, thankfully.
Thankfully.
I'm just running a department. I'm not running a conference at the moment.
Yeah. Well, that's enough. That's quite a bit of work as well. I think that people like Ali who have had to deal with this transition time have really come through in dealing with it.
Absolutely. Yeah, they've done a spectacular job in making it way better than we had any right to hope.
Yeah. Okay, I'm going to go to the next question. So this one is from Sophia Jasupalu. I apologize if that's mispronounced, at Imperial College. Is there a follow-up on the helicopter software verification project? Have the automobile and airplane industry taken notice of the amazing success of this project? And have the lawmakers taken any notice? Maybe you could give us a little bit of background on what that project is.
Sure.
As well.
Sure. So HACMS is a project that I ran when I was at DARPA, and the goal was to use formal methods-based techniques to build software for a couple of vehicles that would be much harder to hack into. So the air team used a quadcopter from Amazon and a Boeing unmanned Little Bird helicopter as the test platforms. And there was a red team whose job it is to try to break into the system. The red team tried to break in at the very beginning of the program, and then at every 18-month period. And at the beginning of the program, they broke in no trouble. They didn't, with remote access, they were able to exploit vulnerabilities in the code and take over complete control of those vehicles. Then the formal methods researchers went in and replaced a lot of the code. They used domain-specific languages to generate code along with proof obligations. They had an architecture language to describe the overall architecture of the system. They proved simple properties about packet formats that packets that were malformed would get dropped, authentication, just sort of simple things. And at the end of the first 16-month phase, the red team got to try attack again. And the red team had full knowledge of the system. They were able to participate in all the design meetings, and they had all the source code of the system. So they knew it really well. But again, they were not they couldn't physically touch the system. They had to wirelessly hack in, and they weren't able to at that point. And then in the next phase of the program, the formal methods researchers applied their same tools and techniques to the Boeing unmanned Little Bird helicopter, which is a helicopter large enough to have 2 pilots or to fly completely autonomously. And they used the SEL4 microkernel from NICTA to create different partitions, a high assurance partition that was controlled talking to the ground station and talking to the flight control computer. All of that was high assurance code, but then there was a low assurance partition where the red team ended up being able to put whatever code they wanted in that partition running at root access. So the red team then was challenged not to hack into the helicopter from the outside, but from code on the helicopter running at root privilege in this partition, break out of the helicopter and break out of that partition and disrupt the operation of the helicopter. And they were not able to do that. And they were so confident that at the end of the program, they allowed the red team to do that attack on the helicopter while it was in flight with the test pilots in the helicopter. So basically, if the formal methods researchers had not done a good job, it was very dangerous for the pilots, but obviously it worked out really well. So, the result of that was that in the National Defense Authorization Act of 2019, which was called the John McCain Authorization Act, the lawmakers directed the Pentagon to explore applying HACM-based technologies in other situations. DARPA has had a number of follow-on programs to use formal methods-based techniques at larger scales and in more kinds of systems. So I think that there's less visible signs of success, but I think that the techniques are starting to get more attention paid to them. The Society of Automotive Engineers has started offering training sessions in using SEL4 and learning how to use SEL4 to leverage it as a sort of exquisite artifact from which you can build a much bigger system where a lot of the system is not developed with formal methods-based techniques. It sort of doesn't matter the quality of that software. It's kind of in the insecure partition, if you can think about it that way. And yeah, you can still have system-wide properties that are guaranteed to hold, even if part of the system ends up being corrupted.
That's very cool. So are you seeing that the courses necessary for people to start using these formal methods more broadly, are those starting to come into play?
So I think we are teaching students more how to use formal methods-based techniques. There are a lot more courses in using, COC and the software foundations materials, for example. I think there are also more courses in using model checkers and things like that. I don't think these kinds of techniques are ones that, like, if you're going to be a programmer, you have to know these techniques. I think there's a whole vast continuum of different kinds of programmers with different kinds of skills. And I think that we don't need all programmers to be able to do this. We just need more programmers who can do this. And I think we are growing that capacity. I think that there's still not as many as we could use. I think Amazon is hiring a ton of these people. Gawa is hiring a ton of these people. There are sort of specialized software shops who are, if you have these skills, they're looking to hire you. So I don't know that there's a huge imbalance at the moment about how much training we're producing versus how much need there is. I think that the tools are still quite challenging to use, and we need to continue to work to make them easier to use, more automated, and more like the work that Peter O'Hearn's worked on at Facebook, being able to include the techniques in a tool chain so that programmers have actionable things to do as part of their normal design process. There's a really cool work that Gawa has been doing with Amazon Web Services on the proof of correctness of the TLS services. So the transport layer security piece of Amazon is incredibly important for their web services business, right? If they want to have companies trust that company A's data and company B's data are not getting interfered with each other, the security of the underlying system is really important. So they built a proof of functional correctness of various parts of the TLS protocol, including the HMAC piece. They leveraged Andrew Appel's work that was published at Usenix Security, proving kind of from the high level principles of security down to like the high level implementation in COC that the cryptography primitives give you what you want. And then what the Gawa and Amazon teams did was mapped that high level sort of functional programming code down to low level performance C code in a way that that part of the proof was automatic. It was a script that developers could go and change the implementation and then rerun the scripts, and the scripts would redo the proof. And over a course of the year, they changed the code and reran the proof. It was something like 967 times, something on that order. And all but 3 of the times, the proof was automatically updated and no further need for any type, the proof just worked. Only 3 times did they have to go get the proof engineer to come back and change the proof of correctness. So I think pipelines like that will be how we start to get more high assurance code into systems. So a large majority of your code, it doesn't really matter if it's super correct or not. It's okay if it is buggy, but there are key parts that if you get those key parts right, then you can have system-wide security guarantees. And that's where you want to put the super high powerful formal methods-based techniques. And then you want to build them in a way that you have this kind of automation pipeline where it can just be redone most of the time without involving the proof engineers. I think that's a pipeline that could give us much better security for in the relatively near future.
Wow, that sounds really neat. I'm gonna ask you now a question from someone that's related. So this is from Julia Belyakova at Northeastern University, and she's asking, do you think improving proof automation is necessary for wider adoption of verification in software development? Or will there be more professional provers whose daily job is to prove things like programmers' job is to write programs? So it's very related to what you just said, but I wanted to ask the question in her words.
Yeah, so I think actually both of those things are going to be important. I think we're going to need to have more proof engineers who could do the hardcore, like the part that Andrew Appel did, for example, and his students, the really scratch your head and figure out how to make this work. And then have more proof automation tools so that you can apply them automatically in a much broader set of contexts. I think we're going to need both of those kinds of skills. And so we need to do both of those things. I think another thing that we need to do that will make a huge difference is change the mindset of who's responsible for mistakes. So, the software industry for a long time has had basically this software is good for nothing. You use it at your own risk. And, if it does happen to do something useful for you, good for you, but we're not, that's surprising to us kind of license versus say the automotive industry where there's a warranty. There's this car will do this for you. And if it doesn't do that for you, the car company is liable. So modern automobiles are computers on wheels, right? They run 100 million lines of code, right? So is it a computer or is it a car? Which industry's liability regime will, in the end, be supreme? And my personal opinion is that it will be the automotive industries, not the software industries. And not all software is created equal. Some software, it's fine that the warranty says the software is good for nothing, but other software is safety and life critical. And in those places, I think it's really critical that we build better quality software and we hold the software manufacturers responsible for the quality of their software. And that if software manufacturers were responsible for paying for the insecurities in their code, then they would be willing to invest more money in producing higher quality code in the first place. I think part of the reason why we have so much low quality software is because the people who pay for the insecurity are not the people who are paying for the software development. If we could get those two interests better aligned with economic incentives or policy incentives, then we would have higher quality software and there would be more demand for formal methods, programmers, researchers.
Yes, I'm sure that's something that not all of us want to hear. We've been pretty fast and loose with programming for many decades now. But as someone who drives a vehicle, not as much as I used to, but still drives a vehicle, I do hope that we have more responsibility of the computer on wheels that we currently have. Yeah. So Santosh Nagarkate from Rutgers has a related question as well. And so I'm going to go ahead and ask that one right now. From your experience overseeing the HACMS project, what do you think some of the barriers are making formal methods mainstream? And you've pretty much answered that one, but he goes on to ask another question, which is, what do we as a community need to focus on, ranging from education to research? So you touched on the education piece already, but what do you think in terms of research should we be focusing on?
Yeah, so research. I think specification, like how do we write down what a system is supposed to do in a way that the specification isn't horribly difficult. I think the combination of verification and validation. So like verification just proves that the code did what the specification said. But if you have a super complicated specification, how do you know that the specification was what you wanted it to be? So that's a testing problem. You have to do validation. So how do you map those up in a way that is efficient and effective as possible? I think there's lots of ways of interesting questions about how do you connect, like a lot of formal methods is in fact fancy search problems. So machine learning is all about fancy search problems. So how can you connect up machine learning based techniques to theorem provers, where obviously once you get an idea, you have to be able to check that it's correct and that you can prove everything. But the search doesn't have to be a provably correct process. It just has to be able to explore the search space in an interesting way to come up with suggestions that you could then check in a rigorous kind of a way. So usability and automation, program synthesis, these are all related pieces that I think there's a lot of good research to be done in that space.
Okay, great, thank you. All right, so switching gears slightly, still mostly technical questions, but now asking about DSLs. So Sophia Josapoulou from Imperial College is asking 3 different questions about DSLs. I'm just going to give you all 3 and let you pick and choose how you want to go for it. You've done a lot of work on DSLs. She writes, was that work driven by the D domain experts or by the programming language experts? And then her second question is there some common theme that applies to most DSLs? And is there some experience? Her third question is there some experience that can feed back from DSL work into PL work?
DSL work is PL work.
Yes, I agree. DSL work is PL work.
Yeah, so in terms of, is it the domain people or is it the PL people? I would say actually what's really important is the partnership between the domain people and the PL people. I think each group of people or kind of people has a perspective and a knowledge that is absolutely critical for the success of the project. That the domain people know what they're trying to accomplish, but often don't have a perspective of how do you design a language, like what is appropriate level of abstraction. So trying to so in the experience of designing Hancock, which is a language for processing streams of transaction data to build customer profiles. So you could think of like profiling phone numbers for fraud activity, for example, which is what it was originally designed for. Talking to the statisticians who were building these per customer profiles, like their level of what they were thinking about was very focused on a per customer computation. So they thought about it at not quite the right level of abstraction. So like we kind of interviewed them and then kind of wrote down something, and it just didn't, it was a kind of a mismatch of stuff. But then when we like looked at it again from, okay, this is the problem they're trying to solve, and these are the key pieces that are important to them. How do we approach it from a programming language perspective? Then we're like, oh, okay, here are the concepts, here are the big abstractions. And then we were able to take what they had told us and come back to them with like, here's some pseudocode. Does this, like, do you think this makes sense? And they looked at like, oh my God, that's the program I was talking about. Like it looked nothing like what they actually were telling us about. But when they saw it, it was like, yes, that. And like, now we can talk about the pieces, like the things at the level that we think about them. They're just directly reflected in the code instead of all of these encodings, right? The encodings all got pushed into the compiler. And what was left at the surface was the abstractions that made sense to them. So it was, the PL without the domain knowledge, we wouldn't have known what problem to solve and what was really important. But the domains people without the PL side just weren't thinking at the right level of abstraction. And I mean, I'd have to go back and look at my notes more carefully to be able to tell that story in a more detailed way. But I think it's really the partnership that's important.
So it's the partnership that's important. And then have you seen some of the solutions that have come about from these partnerships? How have you seen some of those results make their way into more mainstream PL research, I guess? I'm not sure how to refer to it, because you're right, DSL research is PL research.
Right. So I mean, there, I think it's like domain-specific languages allow us to simplify the problem, right? Instead of having to solve the full general case, you can focus on a much smaller piece of the domain, and then that allows you to bring to bear more powerful tools, for example. So like with program synthesis, right? Synthesizing arbitrary programs, super hard problem. But if you're working in a very small domain, very specialized domain, then specifying the search space and the specification of what constitutes a good solution is much, much easier. Similarly, the verification problem can be much, much easier if you're working in a smaller, narrower domain. So in like domain-specific languages kind of allow you to carve off, I don't know, maybe a playground or a simpler space where you have a much better chance of being able to solve some of the problems. I think another problem is, well, okay, now you have all these nice little playgrounds where you can solve the problem in isolation, but how do you get them all to play together? I don't know that we have a good solution for that yet. I mean, one idea is you embed them all in one language, and then that host language, like if that's Scala or Haskell, then you can kind of all play together at the top level. I think there's a lot more work to be done in that knitting together piece. And honestly, in the construction of a domain-specific language, where it sort of feels like, we have tools for describing type systems, and we have tools for describing semantics, and we have tools for describing rewriting systems. Like, why can't we do something more like the SpoofAx workbench, where you can like do all these specifications and then put it together and push the button and have it come out with a really nice implementation that is performant and has syntax highlighting and will do synthesis for you and will prove your property is correct. Like, we're a long way from being able to do that, but it sort of feels like maybe we could eventually with 50 more PLDIs or something like that.
Yeah. Well, and I think some people like Amina Torlak are making some progress with that, with like Rosette and things like that. Yeah. At least the synthesis piece that you mentioned. So I do want to point out that we are past, about 5 minutes past our official ending time, but these have been going on for a while. Pretty much, Kathleen, as long as you're willing to keep answering questions and there's questions, I'll keep asking them. So just let me know if you need to step out at some point. All right. So this is switching to talking about some of the different roles that you've taken on over the years. So this is from Anders Miltner, who's at Princeton. You've worn a lot of hats over the years at industry research, DARPA program manager, and now as professor and chair in academia. What are your favorite / the best parts of each of these jobs?
All right, cool question, Anders. Yeah, so what I like about industry is, particularly, research lab and industry, is that it's quiet. You don't have to do 50 million different things all at the same time. You really can focus on, you can really choose kind of how big a portfolio do you want, how narrow a focus, how broad a focus do you want. I mean, so I really like that. I ended up choosing to have an incredibly broad portfolio and do a million different things as if I were a faculty member, but that was a choice. I didn't have to do that. I also, another really nice thing about working in a research lab is that there are problems all over the place, like that are real problems that are motivated by the company's bottom line, by the way the company runs things. And so it's not hard to find problems that are interesting and relevant. And when I was hired at AT&T, they were thinking of creating a programming language group, and then they changed their mind. So they hired me as the theory part of this group, and then they decided that they didn't want to have this group after all. So like there I was as a programming language theory person without even a programming language group. And yet even so, like, it was not hard to find problems that were of interest in programming language space that I could make a case to AT&T was valuable and interesting to them. So like the Hancock and PADS projects are examples of that. So you have to be relevant to the company, but in some sense, like you only have one funding agency that you have to make happy, which is your company. You don't have to like go and find funding from a whole bunch of different sources and compete with outside people. You're just competing against inside people, and you have a lot of inside knowledge on what the company is looking for. So those are some of the things I liked about being in a research lab. Government there's a huge range of different kinds of government positions, and I can only speak to being at DARPA. What is amazing about DARPA is the amount of autonomy you have as a program manager. So DARPA's mission is detecting and creating strategic surprise. And one of the ways they make sure that they can do that is they're a very bottom-up organization. They look at the program managers to direct what should DARPA be doing. So as a program manager, you go and you make a pitch, which is a 30-minute PowerPoint presentation followed by 30 minutes of question and answer about like, what should DARPA be doing? So like HACMS was, the problem we're trying to solve is cars and other cyber physical systems that interact with the real world are incredibly easy to hack. That's bad, right? We could use formal methods-based techniques to make them much less hard to hack. The existence of the SEL4 microkernel and the ComCert verifying C compiler are evidence that we have some prayer of doing this, that formal methods-based techniques can actually help us build artifacts that are real and large enough to affect the real world. And to do this, I would need a team of about 100 researchers working for 4.5 years, and we will have a couple different vehicles, and there'll be a red team that will test the accessibility, the success of how hard it is to hack into the system every 18 months. I'll need like $80 million. And they said yes, right? So then I got to write the broad agency announcement. I got to read all the proposals. I got to pick which of those proposals I thought were going to maximize the chances of living up to what I basically had told DARPA I thought was possible. And then go through the process. It's like when you're a professor, like maybe an analogy is when you're a grad student, like you're doing your research, you know exactly what works and what doesn't work. Like you kind of know where all the bits are buried. Your level of understanding is very detailed, but kind of at the very bottom level. And then you finish your thesis and you graduate. And if you become a professor, your job is to kind of look up and figure out like, where are we going? And write a grant proposal and get funding, and then hire grad students and then train them to make sure they have the resources they need, that they're making progress, that they're playing well with each other. And you kind of iterate that. When you're a DARPA program manager, it's like one level up from that. Instead of writing a grant proposal, you write a meta grant proposal. Instead of raising $500,000, $1 million, $2 million, you're raising $80 million. Instead of getting 4 or 5 grad students, you're getting 100 researchers from around the world. And so it's an opportunity to have just incredibly long lever arm. You don't get as much credit, you don't get your name on the papers, but you can really change the game and change how things work. So it's an opportunity to make a huge, huge difference. DARPA is also incredibly well organized internally. So there's a lot of staff so that program managers really get to spend their time focused on the problems they're trying to solve and not very much time on stupid bureaucracy, which if you have DARPA funding is probably shocking because DARPA performers actually spend quite a bit of time on stupid bureaucracy. But inside, DARPA has really good techniques for dealing with that. So that's what I really like about DARPA. And then being a professor, I really like interacting with students. I really like teaching. I really like the mission of the university, which is advancing knowledge. That's the sort of feels like the purest expression of kind of what I want to be doing on a regular basis is figuring out answers to problems that we haven't ever thought about before. Yeah, and the part that's the worst about the university is having so many different things to do all the time.
The multitasking.
I don't know, multitasking doesn't seem like sufficient level of multi to capture the level. On the flip side, like it's never dull. There's always something interesting to do.
There's always something interesting to do. Yes, always another meeting too. But so you did have all this variety of experiences from industry to government to academia now. Was this your plan? Was this your plan from the very beginning, or how did this evolve?
Right. So when I was a PhD student, I envisioned being a faculty member. So I spent quite a bit of time when I was a PhD student really looking at what does a faculty member do? So like I served as the bureaucrat at Stanford, which means that I like went to faculty meetings and I actually sat on the executive council of the faculty meetings. I served on a hiring committee for a faculty member. Like I really looked at like, what does this job really involve? And like, yes, this is what I want to do. But the job market when I graduated sucked. And so like when I graduated, I got a full-time position at AT&T Labs Research, which is like an amazing position. And then I got a bunch of postdoc offers. So I'm like, okay, I'm going to go to AT&T Labs. So that's how I ended up in industry. John Ruppy, who was at AT&T Labs at the time, basically called me up and said, like, you should apply. And I was like, well, I was really thinking of academia. What do I have to do to apply? And he's like, oh, just send us the same stuff. So I sent the same stuff and I ended up getting the job there and then going there because it was the best offer that I had at the time. And then I ended up with a 5-body problem. So I had, me and my husband and my ex-husband and his wife and our daughter. And like a 2-body problem is daunting. A 5-body problem is like, we're just going to stay here. But then my ex-husband decided to move to California. So, and Google called me up to ask if I was interested in moving to Google. And this was at a time when AT&T was going through a lot of financial difficulties. So at the time, my husband, my ex-husband and I all worked for AT&T, and my ex-husband's wife was a stay-at-home mom. So all of our family incomes were from AT&T, which was in a precarious financial state. So when Google called me up, I'm like, maybe I'm interested, but only if you interview my husband and my ex-husband. And they were like, okay. So they did, they interviewed all of them. They made all 3 of us offers. My husband took the job. My ex-husband got a job at a different company, Salesforce. And I got AT&T to let me work remotely. So I worked remotely for 6 years. That's when I was a consulting professor at Stanford. And then my daughter went to college. And so I only had a 2-body problem. And that was the point, was like, I've always wanted to be a professor. If I don't switch into academia now, I will never be able to switch into academia because I will be kind of just too far down the pipeline. So that was the point where I applied for jobs. But knowing that I had intended to be a professor, I had worked while I was at AT&T to maintain my viability as a professor. So like I taught classes and got my names on the teaching evaluations. I wrote grant proposals so that I had some record so that when I moved to Tufts, I was actually able to move as a tenured full professor.
And then you got the DARPA offer like after you'd already accepted the Tufts offer, if I recall.
Yeah, that's right. So the move to Tufts took a long time because they had to go through the full normal tenure process. So during that, basically while my tenure process was happening at Tufts, the opportunity to go to DARPA came up. Peter Lee was basically going around the country talking to people about, wouldn't you like to come work for DARPA? And each time he described like what the job was like, it was like, oh, that sounds really cool. So the 3rd time I'm like, okay, I'm interested. I went to Tufts to the dean to ask like, are you interested in this? And they're like, oh yeah, this is fantastic. We're hiring you to raise our research visibility. Having you go to DARPA as a Tufts faculty member is fantastic. So, and they wanted me to go right away because I didn't yet have students and grants and all that. It was easy to just go basically from AT&T to DARPA and then to Tufts.
So it all worked out. Great. Yeah. So I've got another question on the Slack from Alexandra Silva, who's at the University College London. I have a related question to Anders, who asked about what's your favorite parts of all these different careers. Did you feel you needed extra training when switching between roles? And do you have any advice to people who have different roles throughout their career, how to ensure you can do these different roles at a good level?
Yeah, so let's see. In academia, we never get training for the job we actually are doing. We only get training for the last job that we like once you finish your PhD, you really don't get training for anything ever again. Which I think is kind of not so good. I think one of the things that was valuable was being at a company where leadership was really respected and valued. So I think that made me pay more attention to what makes an effective leader. And then I think that translated over into other domains. I think I'm not a terrible leader naturally anyway, but then being in a company where leadership was respected and valued and rewarded helped that development process. I think that it's really valuable to invest in your own professional development about, what skills do you see would be valuable for what you want to accomplish, and work on doing that. So there are like books you can read. So I read various books about leadership. There's training courses that you can take. I did a training course last year about managing groups of people and thinking about how to do problem solving. Just talking about different ways of framing problems. So for example, you can have a symbolic frame, which talks about kind of what ideas mean. I'm not going to explain this well. A political frame about well, I'll do this for you if you do that for me. And then an HR frame, which is about people development and investing in people. And then an org chart frame, which is about you report to me and I report to you. What are the dotting relationships? And that when you're solving an organizational problem, all of those frames have different insights that you can bring to it. So by looking at a problem from those different frames, you can get different insights and different ideas about how to solve the problem. So none of the details of that matter, except to say that there's a lot of resources out there that you can take advantage of and get better. And I think that our research and academia in general would be better served if more people developed their personal and leadership skills and not just their technical skills.
Okay, so there are a lot of questions on the Slack, Kathleen, and so if you have time later, you may not. I have seen some of the AMA guests go back and answer some of them. I'm going to go ahead and just pick one last question that's on a slightly different topic, but about students and about Haskell. So I think that might be a fun one to end on for everyone. Okay, so this is from Artem Pelenitsin, hopefully, Northeastern University. And Artem asks, when I meet students from Tufts, including ones working with you, they say they're having fun to write their projects in Haskell, and I envy them so much. How do you choose languages for your projects when you have the flexibility in that? And do you have a strong preference, or does your choice mostly depend? Oh, this is, whoops, I told you I wasn't going to ask you this question, but they rephrased it. So let me rephrase this project, this question in terms of, so when your students are starting to put together a project, how do you help guide them in terms of choosing the tools that might most effectively work?
Yeah, so it depends on the project that they're working on, and often it's a project that is continuing from or building on some prior work, in which case building in the same tool set as the prior work is there's a huge advantage of that. Also, building in a language where there's local knowledge on how to use that language, so that when you get stuck, there's somebody that you can go ask. It's also really important to build in a language that is comfortable to the person who's building it. I do find that students are stubborn, and they will continue to work in the language they're comfortable with, even if you wish that they would be working in some other language. I mean, this is one of the things, when I became a faculty member, I thought that I would be very hands-on and really, in the trenches coding with my students. A reality of becoming department chair almost immediately after arriving as a professor is I don't have the time to do that. So I'm further removed. So the first answer is whatever the student's going to be most effective in, and where they can get the most resources and help in building whatever it is they need to build. So I don't have I guess I don't have a religious, it has to be this or it has to be that. It's whatever's going to be most effective.
Yeah, and just to give other people a little bit of the backstory, Kathleen and I had talked about ahead of time, what are some possible questions? And she's not a huge fan of the what's your favorite programming language, which I kind of agree, because I feel like I don't really have a favorite programming language. I just use the programming language that I think is going to most help us solve the problem we're trying to solve. And there's lots of factors that go into that. So I'm going to give you another question. So that's not going to be the last question. From the same person, because they may feel they got cheated out of their question not being answered. So Artem also asks, what are you working on right now?
Yeah, so a bunch of projects. So two of them at the moment, I have a student who is working on a verified version of the All-Star parsing algorithm. So verifying that the All-Star parser generator is functionally correct. It's sound and complete and always terminates. Antler All-Star is the parsing algorithm behind Antler 4. So he actually has the proof all finished and is now working on performance measurements, and we will be writing the paper up very soon. So that's been a lot of fun. And then the other project, one of the other projects I'm working on is format inference, so grammar induction for binary data. So with Dave Walker and Yitzhak Mandelbaum and people at Gawa a long time ago, we worked on the problem of, given ASCII ad hoc data formats, can you infer a PADS description? So can you do grammar inference and learn a description that will allow you to parse the data automatically? And at the time we were like, oh yeah, binary data, that's totally impossible. So we're just working on ASCII data because there's tons of redundancy in the ASCII data so that it's sort of people readable. So then a couple of years ago, I was talking with colleagues at Gawa, and they were like, yeah, what about that binary case? And we're like, we have some funding. I have a student for the summer. Let's just see what we can do. So we got some challenge data and the challenge, like over the summer, what could we figure out about this data? And we shocked them how much we could figure out about the data. So it turns out that like integers don't look like floats in binary. Integers have kind of a step pattern to them, whereas floats are smeared out, so they take most of the bit space. Yeah, and we have a whole toolkit of different kinds of approaches to be able to reverse engineer the format of binary data. So the assumption is we're packet data, binary data, a clean sample. So all of the packets come from the same protocol, although they don't have to have exactly the same format. You can have tags in different length fields. We've made a lot of progress. So the student working on that is working on writing that up this summer. So hopefully you'll be able to read about that in more detail in the relatively near future.
All right, great. Well, as we wrap up here, Kathleen, is there anything else you'd like to say?
I should say that the student working on that is Jared Chandler, and the student who is working on the proof of correctness of All-Star is Sam Lasser.
All right.
And, yeah, thank you for your time. I appreciate your attention, and I hope you're all really enjoying this online PLDI experience.
Yes, and thank you so much for your time and telling us so much about your research and your career. It was really interesting.